We are now in position to take on our final and most difficult challenge. Using all that we have established so far, plus some additional clever insights from Feynman, to prove that a planet's orbit is an ellipse. We start with our position diagram and ask, what might a non-circular orbit look like? Could it be a polygon of some sort? Probably not. In reality, we expect gravity to act continuously, so we expect a smooth curve. Could it be some irregular closed curve? I call this the fried egg. It seems unlikely that the laws of nature would produce an orbit that appears to wander in such a random fashion. Could it be a more regularly shaped closed curve? I call this the deviled egg. It is symmetric in shape and has the advantage that it is not an ellipse. After all, we don't want to simply assume that the orbit is an ellipse. So let's take the deviled egg as a candidate. Let's divide the orbit into 8 wedges, all with a 45-degree central angle. Obviously, the wedges are not all equal. Let's take 2 non-equal wedges, make each into a triangle, and then compare them. We will call them triangles 1 and 2. Let's pull them out of the orbit diagram for a moment and superimpose them. With their central angles lined up. We can change the shape of the larger triangle slightly by giving it a new base. So that the new base is parallel to the base of the smaller triangle. We do this in such a way so that we don't change the total area. We lop off a little bit of area, shown here in blue, and we add in the same amount of area on the left, also shown in blue. And voila, 2 similar triangles. Again, we are using geometry to make some approximations, but always remember that we can make the central angle smaller and smaller so that our approximations, at least we might expect, will become closer and closer to reality. It is a theorem in geometry that the areas of 2 similar triangles are in the ratio of the squares of the corresponding altitudes. Here is the altitude of the smaller triangle, R1. Altitude of the larger triangle, R2. At the top left here, we see that theorem I just mentioned stated in equation form. In other words, the area of triangle 1 equals some constant R1 squared, and the area of triangle 2 equals that same constant times R2 squared. Here I'm showing delta T1 and delta T2, and of course they are not equal, but they are each directly proportional to the corresponding area swept out. This is in accordance with Kepler's law. I leave it to you to convince yourself that the statement, the planet sweeps out equal areas in equal times, is equivalent to saying that delta T is proportional to the area swept out. So if delta t is proportional to the area swept out, and the area swept out is proportional to r squared, then delta t is proportional to r squared. Earlier we showed that for circular orbits, f is proportional to 1 over r squared. We are going to assume that it is also true for all orbits, and if this assumption leads us to a prediction that is confirmed by Kepler's observations, then we can deduce that this assumption is correct. Now, since force equals mass times delta v over delta t, we can see that delta v over delta t is proportional to 1 over r squared. So now we have these two statements of proportionality shown at the bottom here, and we can combine them by multiplying the left sides and multiplying the right sides. It's easy to see that the delta t's on the left and the r squareds on the right cancel out. So we are left with that delta v is proportional to 1. In other words, the magnitude of delta v is constant for equal changes in the angle of azimuth. So let's assess where we are. Here's our hypothetical orbit. At every point along the orbit, planet Q has a certain velocity vector. I've drawn just 2 of them here, chosen at random. The point I want to make is that each velocity vector is likely to be distinctly different from all the other velocity vectors in terms of direction and magnitude. And the differences between one vector and another are hard to predict, unlike the situation, as it turned out, in a circular orbit. However, all of the vectors share one common feature, which I illustrate here by extending the tails of these 2 vectors. That common feature is that the vectors are all tangent to the curve of the orbit. To have it otherwise would be a logical impossibility. The direction of the velocity vectors determines which way the planet goes in the next instant. If the velocity vector is pointing one way and the planet moves in a different direction, there is something wrong with your analysis of the physics. As you will see, this property of tangency will be an important test to see if our later analysis is correct. But again, for the most part, each velocity vector is different from all the others, and we can't predict how it is going to differ from the one right before it and the one right after it. In contrast, we just showed that all of the delta v's are of the same magnitude, and they all point toward the sun. You can see the 8 delta v's that I have drawn in here, including the one that I labeled delta v sub 7. But you can imagine a very, very large number of delta v's, perhaps a googol of delta v's at each point of the orbit. We can move these 8 delta v's into velocity space and arrange them like so. Just as in the case of the circular orbit, we have created a regular octagon, which we call the delta v octagon envelope. Wait a minute, you say. This is starting to look exactly like the velocity diagram we got for a circular orbit. How can that be? After all, these delta v's back in our position diagram are not symmetrically arranged in physical space. But that is the magic of velocity space. Again, you can move vectors around in velocity space wherever you want, as long as you don't change their relative magnitude and relative angular orientation to each other. This is the beauty of Feynman's insight. But we can do even better than this if, back in our position diagram, we divide the orbit into a googol of segments of equal angle. Then we can collect a very large number of delta V's, or should we say dV's. And just like in the case of the circular orbit, by laying down each dV in sequence head to tail, we can create a regular polygon of infinite sides, and we again have our dV circle. And if you are concerned that we are just going to wind up with a circular orbit again, just wait and see. To move forward now, what we need is at least one velocity vector from which to derive all of our other velocity vectors. What to do? Well, consider that the speed of planet Q is going to be a maximum when it is closest to the Sun. Why? Well, it follows again from Kepler's second law. It also follows from the conservation of angular momentum and from the conservation of energy. But Newton didn't use those arguments, and neither did Feynman. We will label that point where planet Q is closest to the Sun as 0 degrees. And we will call its velocity here Vmax. I have extended the tail here just to remind you that Vmax must be tangent to the orbital path. And not only that, let me enlarge the diagram. The direction of Vmax must be perpendicular to the orbital position vector r at that point. I label it r min to remind us that planet Q is at its closest approach to the Sun. Why does Vmax have to be perpendicular at this point? Well, let's zoom way in, and let's say Vmax makes an angle of 89 degrees with r min. And let's look at a very, very short segment of its orbital path, 1 degree. Then what is the third angle of this triangle if the Sun is a distant vertex? The remaining angle must be 90 degrees, because the angles of a triangle have to add up to 180. But if this is a right triangle, then r min is the hypotenuse, which means it is the longest side of the triangle and longer than r1. But this contradicts our premise that r min is shorter than any other radius vector. Because of this logical contradiction, we know that the angle cannot be less than 90 degrees. What if the angle between Vmax and r min is greater than 90 degrees? Let's say 91 degrees. Okay, but if we extend the tail backwards over 1 degree of orbital angular trajectory, we again form a triangle. And once again, we form a right triangle with r min as the hypotenuse, which means that r min is longer than r359, shown here. And again, this logical contradiction tells us that the angle between Vmax and r min cannot be greater than 90 degrees. So here's our Vmax, and let's take it out of the position diagram and move it into velocity space. Here's our dv circle in velocity space with 0 degrees at the top corresponding to time equals 0, which in turn corresponds to time equals 0 on our position diagram when planet Q is at 0 degrees azimuth traveling at V max. We bring in V max and the question is where exactly to put it. Well, we can't change its direction, so we have to line it up along the vertical diameter of the dv circle with its tail below the center of the circle and its head resting on the dv circle at 0 degrees. Let's label the tail of the vector O for origin. Now we have our velocity vector factory. Let's say we want to find out the velocity vector at 45 degrees azimuth. First, we measure out 45 degrees along the circumference of our dv circle. Then we draw a vector from O to the point on the dv circle at 45 degrees. We can measure the directional angle of the new vector. It's 31 degrees reference to Vmax on this velocity diagram, and therefore it is at 121 degrees referenced to 0 degrees on the position diagram. So let's move this vector that we just made over to the position diagram. And let's put its tail right on the 45 degree azimuthal line. The only problem here is we don't have the r coordinate because r is not a constant. So we don't know whether to put it here or here or here. Of course, we can make a rough approximation because we know we are trying to produce a smooth curve, but we just don't know exactly where to put it. Before we tackle that problem, let me make one observation. Notice that although our little velocity vector factory in velocity space will give us the relative magnitudes of the different vectors, the magnitudes don't really matter too much. We're simply using the vectors and their directions to determine the point of planet Q at each angle of azimuth. We are using the intersection of each velocity vector with the corresponding angle of azimuth to determine the position of Q at that particular angle of azimuth. So determining that point of intersection is now our key problem. And you can play around with the velocity vector factory, that is the dv circle in the velocity diagram, and manufacture as many velocity vectors as you want. For example, you could find the vector for an azimuth of 147 degrees. And here it is. You can then move it into the position diagram, and as you add more and more vectors, you can start to construct an approximate orbit. But it is a very cumbersome and tedious process, and you will see that you need a lot of data points before you start to even get close to a smooth curve. What if there were a faster way to add in velocity vectors and to add them in according to some automatic rule that determined a consistent way to position each vector along the corresponding azimuthal line. Here again, Feynman comes up with a very clever solution. We can see that one of the problems we face in this regard is that on our orbital position diagram, 0 degrees azimuth is at 3 o'clock, whereas on our velocity diagram, 0 degrees is oriented at 12 o'clock. Of course, we set it up that way so that Vmax was pointing straight up in both diagrams. But what if we took our velocity diagram, rotated it 90 degrees clockwise, and superimposed it on our position diagram so that the center of our dV circle is right where the sun is located? Of course, now all the velocity vectors are rotated 90 degrees clockwise, but we can fix that by drawing perpendiculars to every velocity vector and noting where they intersect with the corresponding azimuthal line. Although we still don't know where exactly to position the perpendiculars along the azimuthal line, we can experiment with different rules and see where they lead. The most obvious rule to try first would be to position the new perpendicular velocity vector right at the head of the original velocity vector. And this is exactly what I have done here. However, as we add in even just a few additional vectors, we immediately see two problems. First of all, we see that the intersection of each vector with the azimuthal line traces out a circular orbit, something we were trying to avoid. Secondly, the new perpendiculars are not tangent to that orbit trajectory. Once again, Feynman comes up with a very clever solution. Here is our position diagram once again. And once again, we superimpose our rotated dV circle with Vmax in its new orientation. And we are going to draw in the perpendicular vector at the midpoint of Vmax. In so doing, we create a perpendicular bisector to the original Vmax and create a new Vmax with its orientation back in the proper direction for the position diagram. And notice once again that we are not worried about the magnitudes. We are only worried about keeping the directions correct and noting where each vector intersects with the corresponding azimuthal line. Left a little black dot to mark the position of planet Q at 0 degrees azimuth. We move on to 15 degrees azimuth. We draw in the new velocity vector. We draw in the perpendicular bisector, and we note where the perpendicular bisector intersects the 15-degree azimuthal line. We mark that spot with another little black dot representing planet Q as it traces out its trajectory. We continue on another 15 degrees of change in azimuth and repeat the entire process, hoping that this will turn out to give us enough data points to construct the shape of our orbit. So watch what happens as we repeat this process every 15 degrees of azimuth. It looks like an ellipse, doesn't it? Well, let's see. I'm going to make a green ellipse. I start with a green circle. I stretch it out in one direction. And I stretch it out in the other direction. And indeed, it looks like we have created a green ellipse that closely matches our data points. Now, undoubtedly, Feynman knew exactly what he was doing. He knew that this technique that we just used was in fact, or is in fact, one way to draw an ellipse. So, was he cheating? Did he stack the deck in favor of winding up with an ellipse? Well, he wasn't cheating exactly, but he took a shortcut. Remember, this solution still has to pass the test of tangency. That is, we will need to show that every velocity vector that we draw in at every point has to be tangent to the orbital path. Before we apply the test of tangency, however, let me show you that this method of drawing in the perpendicular bisectors is guaranteed to produce an ellipse. Let's pick any point D along the dV circle, at whatever azimuth that happens to be. Add in the velocity vector. Label the midpoint of the velocity vector E and draw the perpendicular bisector. Mark the intersection with the azimuthal line with a black dot and label it C. And draw in two new lines, OC and SC. Notice that OC and DC are equal because every point along a perpendicular bisector is equidistant from the endpoints of the original line. And let's add SC to both sides of the equation. So SC plus OC equals DC plus SC. But DC plus SC is just r, the radius of the dV circle, which of course is constant. So no matter where we put our velocity vector, SC plus OC is going to be a constant. Of course, that means we have just defined an ellipse where O and S are the foci and C is any point on the ellipse. In other words, SC plus OC equals R, and we can say that it is also equal to 2A, where A equals the semi-major axis of this ellipse that we have just created. But are the velocity vectors always tangent to the orbital path? This is the final test to see if our analysis is correct. Let's go back to this diagram and add a point Q along the perpendicular bisector somewhere other than C. And note that SQ plus QD has to be greater than SD because SD is a straight line and the shortest distance between 2 points is a straight line. But we have already shown that SD just equals R, which equals 2A, whereas QD equals OQ, and we can therefore substitute OQ into our inequality for QD. And we thereby prove that SQ plus OQ is greater than 2A, which means that Q must lie outside the ellipse that we have just defined. It doesn't matter where we put Q. We can make the same argument to show that Q always lies outside the ellipse. So if every point along a perpendicular bisector to any given velocity vector is outside the ellipse, except for point C, which touches the ellipse, then the perpendicular bisector is tangent to the ellipse. And with that final flourish of insight, Feynman clarified Newton's reasoning and proved that the orbit of a planet is always an ellipse.